Right, so this is section 9.4 of your text in Holt for Physics. We're talking about gas laws. Yesterday you saw a video on gas laws by Hewitt, and hopefully it's quite familiar from the side of chemistry. You might recall from chemistry that we had an ideal gas law that said PV equals nRT, where P is the pressure, V is the volume, N is the number of moles. Don't worry, we don't need to use moles too much anymore. R is that ideal gas constant. And T is our temperature, and that's, remember, it's going to be in Kelvin. Remember then to go between the two, so you'll take your Kelvin as Celsius, and Celsius temperature, when we think of it as absolute zero, it's 0 Kelvin, so you have your Celsius is negative 273 Celsius. So if you take Kelvin minus 273, you're going to have your Celsius temperature. Degree sign, because you can have positives and negatives with Celsius. No degree sign for Kelvin, because it's what we call an absolute temperature scale. So then if we put in 0 for Kelvin, 0 minus 273, negative 273, and so that checks out. Well, in physics, we use a similar equation, but it's called the equation of state. Because substances are then said to be at a certain state of matter. And the only real difference here, there are two. First of all, pressure, volume, same but different units. Instead of the number of moles, we're going to do big N, and that stands for the number of molecules or atoms, particles, if you will. Okay, and then we're going to put in a constant. Instead of R, it's going to be KB, which is the Boltzmann's constant, and the Boltzmann's constant should be in your book, 1.38 10 to the minus 23, so it's a small number. 1.28 10 to the minus 23 joule per Kelvin. Just a second here, I gotta double check that number. 1.38 10 to the minus 23 joule per Kelvin. That's right, okay. 1.38. My eyes are playing tricks on me, sorry. Okay, and our temperature T, that of course is going to be in Kelvin again. Pressure. Remember, pressure units are pascals, and for physics, instead of liters, our volume is going to be in cubic meters. Okay? You can manipulate this equation knowing something about masses and molar masses and so forth. On page 339, they show a little derivation where one can say that the pressure of a gas is going to be the density of the gas, rho, times kBT, over little m, and that m, I think, should be probably in kilograms, okay, because density is kilograms per cubic meter. Okay, so what do you do with that? Well, you might remember that the equation of state, now the ideal gas law from chemistry last year, allowed you to make some relationships between properties. One of those, if these are constants, if you hold those two values constant, then what you really have is a complex constant. We could call it just K, or let's do it C, because that makes sense. So PV is equal to C times T. That tells you that the ratio of the product pressure, volume to temperature will always be a constant. In other words, at one set of conditions or state, that product quotient will have a constant value. At another set of conditions, we have to have the same constant of proportionality, and so the product quotient will be the same. What that means is that at one instance, P1 V1 over T1 has to equal P2 V2 over T2. Again, pressure in pascals, volume in cubic meters, temperature in Kelvin. So remember too that you have some graphical sorts of things you can do, and you can make a list of assumptions. Well, if we assume that the temperature is constant as well, as the number of molecules in Boltzmann's constant, then you have P1 V1 equals P2 V2. You might remember that as Boyle's law. Boyle's law relating pressure and volume. And because it's a product equals a product, that's an inverse proportion. So if you were to graphically represent it, it would look like this. That might be jogging your memory. If the pressure is constant, then you have V1 over T1 equals V2 over T2, and that's a direct proportion. So graphing volume and temperature would look like that. And conversely, then if the volume was constant, pressure to temperature, another direct proportion. You see, those two are the same in terms of how they're arranged. So pressure, temperature, and again, a straight line up and away. So one inverse proportion and two direct proportions. Okay, so in terms of solving problems, how does this work? Oftentimes, more than not, you're going to use that equation right there. The text that you are working with here is not really getting into the real hardcore problems involving numbers of atoms and Boltzmann's constant. It really is going to be relating the three variables to each other in one set of conditions and then another. I'm going to pull an example, not 9E on page 340, but I actually have the teacher's edition and it's got a couple other examples. So you can follow through on problems 9E in that sample set, but let me give you another one. We have a sealed tank with a volume of 0.1 cubic meter. So I'm just going to draw that as a box. We'll say that's 0.1 cubic meter. Well, that's a volume, isn't it? It's sealed. It's sealed. So that means the volume won't change. This problem says it contains air at 27 degrees Celsius. Whenever I hear a number, I just write it down and I identify it with a letter. That's the first time I'm seeing a temperature, so I'm going to call it T1. It has a corresponding pressure of 1.8 times 10 to the 4 Pascal. Then it says there's a safety valve and it can withstand pressure up to 5 times 10 to the 4 Pascal. That's a second pressure, so that's 5 times 10 to the 4 Pascal. And it wants to know, will the valve hold if the air inside the tank is heated to 227 degrees? Okay, so hang on a second. This is 227 degrees Celsius. And now we're looking at this in terms of a pressure withstanding. So at first I was a bit hasty. This is when the valve breaks or blows and the tank has to empty. Okay, so this really is going to be our unknown in the problem. We want to see if changing the temperature to that value creates a pressure that's close to 5 times 10 to the 4. Okay, first thing, always convert temperatures to Kelvin. It's simply more convenient, I think, and it saves trouble, especially if you have negative temperatures. If you have negative temperatures, solving the equation could give negative volume. It can't happen. So doing it this way, if you put it into Kelvin, we're going to be in better shape. So 273 added to this one, let's see, that's 473, that's 500, isn't it? Okay. Remember, X is going to be P2. That's what we're looking at. Volume doesn't change. So in our equation, P1 V1 over T1 equals P2 V2 over T2. Since the volume doesn't change, you can ignore it, right? It doesn't become zero. It's just not important to us. So we can just ignore it. So let's solve for P2. Multiply both sides by T2. So that's going to be P1 over T1 times T2. Okay, so pressure 1 is 1.8 times 10 to the 4 Pascal. T1 is 300 Kelvin. T2 is 500 Kelvin. And now just a quick bit of arithmetic here. 5 over 3, I might even be able to do that in my head, but I'm not going to try it this time. So I get 30,000 pascals, which is 3 times 10 to the 4. Sorry, 3 times 10. to the 4 Pascal. Let's see. Will the valve hold? Oh, I got to read the question. Will the valve hold if pressure does not exceed 5 times 10 to the 4 Pascal? Okay, so our answer here, 3 times 10 to the 4 Pascal, that's less than 5 times 10 to the 4 Pascal. And so the answer is yes, it will hold. So it doesn't blow. The valve does not go. Okay. One more example then. We have a weather balloon. Okay. And that weather balloon has a volume of 8 cubic meters. And that's at a temperature of 300 Kelvin at atmospheric pressure. Atmospheric pressure. Okay. The balloon rises to an altitude where the temperature is 200. Okay, so a new set of conditions. 200 Kelvin and the pressure is half atmospheric. We want to know what the new volume is. Well, if you look at the relationships here, P1 V1 over T1, P2 V2 over T2, you got 3 variables, so it's really hard to make a prediction. If the temperature goes down, the volume should go down because that's a direct proportion. This is going to be 200 Kelvin. But you have a confounding factor of a change in pressure, atmospheric. Now it's going to be half of atmospheric pressure. So you really can't make predictions at this point, but we could guess. I don't know. Maybe it's going to be bigger. Let's see. Maybe the fact that you're dropping pressure by half, and that should double the volume, and it's not a very large temperature change, maybe that should shrink it a little bit from where it should be doubled. So maybe somewhere between, I don't know, 16 and 10. We'll see. We can check it, right? So we want to find what this new volume is here in this set of conditions when it's 200 and a half atmospheric. So we've got our equation P1 V1 over T1, P2 V2 over T2. We're not told what atmospheric pressure is. You could look it up. We could put a numerical value to it, 101,000. I think that's what your author uses. And so what's 101,000 divided by 2? I'm not trusting my mind here tonight. 50,500. So you could use those numbers, or you could just say this is P, and that's half of P, right? So for P1, it's just going to be P1. V1 is 8. T1 is 300. Okay, P2 is half of P1, right? Times X, which is our unknown, or V2, and that's going to be over 200. Okay, so the P's drop out because they're the same. This is just half of that. So now we're going to have cross multiply, right? 200 times 8 is 1,600, and half of 300 is 150. So V2 is going to be 1,600 over 150. And that's equal to 10.7 cubic meters. Okay, so our guess, we're a little on the low side, but we were sort of within the range, right? Your text has 11 for the answer, but they're rounding with significant digits. Okay, so what that leaves for us then, on page 341, I'll put this up on the board for you as well, our practice 9E, and that's going to be all 1, 2, and 3. There's only 3 questions. It shouldn't be too bad. We'll give it a try. And remember, the odds are you're going to get 2 of them. Hope you have a nice day.